Hello everyone, welcome to 3 Deviations. In the last video we covered finding the area in between curves as a region, where we need to find the intersection between a parabola and a cosine curve. Well, now we'll take a little bit more of an algebraic approach and find the area in between parabolas in the region created by a pair of parabolas. And this will require, again, a little bit more algebraic thinking as opposed to the more graphical thinking that we did with the cosine wave and the parabola. All right, so now I would like to begin our example. So this time I want us to find the area in the region bounded by 12 minus x squared and x squared minus 6. All right, so first what's going to be important is that we determine where our zeros are and also where our intersections are. The zeros are more important for the graph, and then the intersection, of course, is the most important for our integration, although the zeros are more just to make sure that our sketch is accurate. All right, so let's find our intersections. And we do this by setting our two polynomials equal to one another. So this would be the case with any other type of algebraic function that you have. So if you're finding the area between two algebraic functions, set them equal to one another, and they should be solvable. Again, with trig, it gets a little bit more complicated, but when we're using this with polynomials, logarithmics, or exponentials, it's fairly easy to determine where the intersections are algebraically. So we are going to set negative x squared plus 12 equal to x squared minus 6. All right, so now we are all set with our equivalents, and now all that's left is to solve for x. So that leaves us, once we combine like terms and put them on one side, set them equal to 0, that gives us 2x squared minus 18 is equal to 0. Then we have x squared minus 9, or x squared is equal to 9. And of course, that leaves us with x being equal to plus or minus 3. So now we have our intersection points being plus or minus 3. Now let's take a look at a graph. Let's graph these functions, and we'll take a peek at what our region looks like. All right, there's our coordinate axis. So for the first graph, let's do 12 minus x squared. So I like looking at it in this way because this shows us immediately that our parabola is going to be opening downwards. And it also shows us where our y-intercept is going to be, or our maximum value, which is going to be at positive 12. So we already know that our maximum value is going to be here at positive 12. So now we can graph our parabola like so. And there is our nice parabola there. All right, so now what we are going to do is we are going to graph our second parabola. And this parabola is x squared minus 6. Now this is super easy to graph because now we know where our minimum is, and because it's a positive x squared, we are opening upward. So there is our minimum value, and now we are going to draw our parabola here and give us our defined region. These were roughly equal to one another. All right, so here we have minus 3, and here we have plus 3. And what's important is now we know our integration areas. So that is our region. So what's important now, again, as I always say, we need to be sure we know what order we're doing things. So on the top here, we have the 12 minus x squared. And on the bottom, we have the x squared minus 6. So now we are ready to perform our integration between negative 3 and 3 between these two parabolas. All right, so the area is going to be equal to the integral between negative 3 and 3 of 12 minus x squared minus x squared minus 6 dx. Now, both of these functions are even. They're both parabolas, so we can apply that nice integration trick where we can set that equal to 2 times the integral between 0 and 3, and then we can combine some like terms, and that gives us negative 2x squared plus 18 dx. Now this is a super easy integral to solve. All we need to do is apply that reverse power rule and evaluate using the fundamental theorem of calculus. that leaves us with the area being 2 times negative 2/3 x cubed plus 18x evaluated between 0 and 3. All right, so that gives us the area being equal to 2 times negative 2/3 times 3 cubed is 27, plus 18 times 3 is 54. And that's subtracted from 0, of course, because the x term being evaluated at 0 kills the whole expression. All right, and now once we evaluate all of this, that gives us an area equal to the value of 72. All right, so that is how you solve really any area between curves problem. This is the hardest one that you'd come across because this is one where you need to actually solve algebraically for those intersections. And maybe they'll throw a substitution rule in there at you, but then that would make it fairly hard to find the intersections. All right, so in the next video, we're going to move on and we're going to start talking about solids of revolution. That's where we think about finding the area in between a region, and then we rotate it about an axis, and then that will give us a volume. So we're moving on to volumes pretty quickly. All right, so we will see you then.